For billions of years, our sun has been the engine of everything. The warmth on your skin, the food on your plate, the air you breathe, all of it powered by one star. But what if that star went silent? What if, instead of a blazing sun, Earth orbited something cold, dense, and dead? It sounds impossible, but science says it might not be. And what would happen is stranger, darker, and more fascinating than anything you can imagine. To understand what could be, we first need to understand what dies. Stars don't live forever. Even our sun, 4.5 billion years old and still burning strong, has an expiration date. When a star runs out of fuel, it doesn't just switch off like a light bulb. It goes through something dramatic, something violent. Depending on its size, it might swell into a red giant, collapse into a white dwarf, or explode in a supernova and leave behind one of the most extreme objects in the universe, a neutron star. Or worse, a black hole. These are dead stars, or what's left of them. Cold, dense, some still faintly glowing, others completely dark. And here's the thing that surprises most people. Planets can survive this death. In fact, we've already found them. Worlds orbiting white dwarfs, planets circling neutron stars, ghost worlds drifting around the remains of something that used to shine. So the question becomes real. What if Earth were one of them? Let's start with the most likely dead star scenario, a white dwarf. When a star like our sun exhausts its hydrogen, it expands into a red giant, swallowing its inner planets, then sheds its outer layers and leaves behind a tiny, incredibly dense core. That core is a white dwarf, about the size of Earth but containing the mass of an entire star. No nuclear reactions, no new energy being generated, just a slowly cooling ember radiating leftover heat into space. Now, imagine Earth somehow surviving this process, pushed outward by the expanding star, settling into a new orbit around this faint, dying core. At first, it might not seem so different. The white dwarf still glows. It still gives off light and heat, though far less than our current sun. If Earth orbited close enough, temperatures could still support liquid water. Scientists call this the white dwarf habitable zone. And yes, it exists. But here's where it gets complicated. A white dwarf doesn't stay warm forever. It cools down, slowly, over billions of years. It fades from white to yellow to orange to red. Eventually, in theory, it becomes a black dwarf, completely dark and cold. Though the universe isn't old enough yet for any black dwarf to actually exist, so life on Earth orbiting a white dwarf would be living on borrowed time. Billions of years of slowly dimming light. Sunsets getting darker every million years. Seasons growing colder across geological ages. And that's not the only problem. White dwarfs are unstable in a very specific way. If Earth's oceans evaporated, if comets crashed nearby, if any material drifted too close to the white dwarf, it could trigger something called a nova, a sudden, violent explosion of light and radiation. Not enough to destroy the star, but absolutely enough to strip away atmospheres, to boil oceans, to reset the clock on any life trying to survive. Living near a white dwarf means living next to something that could suddenly flash with the energy of a billion suns without warning. But white dwarfs are gentle compared to the next option, a neutron star. When a massive star, much bigger than our sun, dies, it doesn't leave behind a quiet ember. It explodes, a supernova, one of the most powerful events in the known universe. And what remains is a neutron star. A city-sized ball of matter so dense that a single teaspoon would weigh 1 billion tons, spinning hundreds of times per second, radiating beams of electromagnetic energy like a cosmic lighthouse. We call those pulsars. We've actually found planets orbiting pulsars. The very first confirmed exoplanets ever discovered, back in 1992, were orbiting a pulsar called PSR 1257+12. Dead star, real planets, proof that worlds can survive stellar death. But could life on Earth survive in a system like that? The radiation alone would be catastrophic. Neutron stars blast out X-rays, gamma rays, and intense particle winds in all directions. Earth's magnetic field protects us from our sun's relatively mild solar wind, but a neutron star's output would overwhelm any natural shield. The atmosphere would be slowly, then rapidly stripped away. The surface would be bathed in radiation that breaks apart DNA, sterilizes rock, and turns oceans into vapor. In short, Earth orbiting a neutron star would be a silent, irradiated rock. Beautiful from a distance, perhaps, deadly up close. And then there is the darkest possibility of all, a black hole. Not the supermassive giants at the centers of galaxies, but a stellar mass black hole, the collapsed core of the most massive stars, an object so dense that not even light can escape its grip. Could Earth orbit a black hole? Yes, in theory, perfectly safely, as long as it stayed far enough away. A black hole doesn't suck in everything around it. It's not a cosmic vacuum cleaner. If our sun were suddenly replaced by a black hole of the same mass, Earth would continue orbiting normally, just in complete darkness. And that is the haunting part. No sunlight, no warmth. The oceans would freeze within weeks. The atmosphere would begin to collapse, gases turning to ice, settling on the frozen surface. Earth would become a dark, silent, frozen world drifting through space around an invisible point of gravity. No seasons, no photosynthesis, no life. Unless, perhaps, something else provided energy. Here's where science gets genuinely surprising. Around black holes, there is sometimes an accretion disk, gas and dust spiraling inward, heating up from friction, glowing brilliantly. Some accretion disks release more energy than entire galaxies. Could a planet orbiting at the right distance receive enough radiation and heat from this disk to stay warm? Theoretical physicists have actually modeled this, and under very specific conditions, the answer might be yes. A planet orbiting a black hole with an active accretion disk could sit in a habitable zone, receiving steady energy from infalling matter rather than from nuclear fusion. It would be an alien kind of warmth. The light would be different, ultraviolet heavy. The sky would glow with a strange brilliance. Time itself would pass slightly differently due to the black hole's warping of spacetime. Every year on that world would be slightly shorter than a year measured far from the black hole. Interstellar, the film, explored this idea, but the physics behind it is real. So why does any of this matter? Because stars die, all of them, including ours. In about 5 billion years, our sun will begin its own transformation. Red giant, planetary nebula, white dwarf. Earth as we know it will likely be consumed, or at minimum rendered completely uninhabitable. But humanity, if it still exists, might not disappear with it. Understanding how planets survive stellar death, how life might adapt to the faint glow of a white dwarf, how energy could be harvested from the most extreme objects in the universe. These aren't just thought experiments. They are the questions that could determine whether intelligence in this universe has any chance at a truly long future. The dead stars aren't just endings. They might be beginnings of a different kind. What if Earth orbited a dead star? It would be darker, colder, more dangerous, but maybe, just maybe, not entirely without hope. Because life, as we keep discovering, finds a way into the strangest corners of the universe. And the universe, even in its oldest and darkest places, is far from finished surprising us. If this made you look up at the night sky a little differently, you're not alone. Like, subscribe, and come back, because the universe still has so many secrets left to tell.